Hello, everybody. Today we're going to do another application of magnetism that's actually kind of important, especially for forensics, for those that have taken it or are planning on taking it. We do something called the velocity selector and mass spectrometer. It is one of the many applications of magnetism. So basically what we're going to start with is two charged parallel plates. One of them will be positive, one will be negative. And I know it's been a little bit of time, but hopefully you remember that between two plates, one positive and one negative, is probably an electric field. And I hope you also remember which way that would point. Remember, what would a proton do? I know we're not supposed to say proton, but what direction would a positive charge go if you released it between these two plates? And the answer is down. So we have an electric field that points down. What we're going to do is we're going to shoot a positively charged particle into this electric field. Now, back in the day, previous topic, this was a projectile problem. Thankfully, we will not be doing that here. This particle is actually going to continue to go straight through. Okay. Now, the question is, how does this happen? Well, it turns out there's a magnetic field. And the only way that can happen is if we draw a free body diagram of this particle, we'll say like right here. We know that the electric field will apply in a force down. So that's F electric. And if it's going straight, hopefully you know that means there has to be a force up. Now that force up is going to be caused by a magnetic field. So that will be our magnetic field. It'll be an FB, which means we have to introduce a magnetic field. Sorry, it should be FB, not B. So, charged particle moving to the right with a force up towards the top of your screen. Which way are your fingers pointing, which is the magnetic field? Take a second for yourself to do that. Again, we're trying to figure out what is the direction of the magnetic field. Particles moving right, force is up towards the top of your screen. Which way are your fingers? They should be into the screen. If you got out of the screen, put down your pen or pencil and use your right hand. No offense, lefties. Lefties have it better for this. So our magnetic field is into the board, or excuse me, into the screen. These fields are actually crossed. This is something known as crossed electric and magnetic fields because they are 90 degrees to each other. One is down towards the bottom of the page and one is into the page or into the screen. So this thing's moving straight. What does it mean about its vertical acceleration if it continues to go straight? Hopefully by now you've said the acceleration must be zero. So that means the sum of the forces in the y-axis for this particular part of the problem must be zero. If this particle continues to go straight, does not go up or down, that means these forces must be equal. We're saying that the magnetic force and the force of the electric field must be equal to each other. Hopefully you also know which equation to be using here. Is this Bill or BQV? Is it a wire or a moving charge? Literally, QV, charge moving. I think you know. BQV, this will be sine 90 again because it's perpendicular. The velocity is perpendicular to the direction of the field, so that's just one. And I know it's been a little bit of time, but the force of an electric field on a charge, Fe equals EQ. And I realize that one of these is a big Q and one is a little q, but either way, it's the same Q, it's charge. So we're left with BV equals E, or V is the ratio of the electric field to the magnetic field. Please do not memorize this. This is not an equation. And by this, I mean this at the bottom here. It's not an equation. It's the result of setting two forces equal. The main point is that this is moving straight. It's not accelerating up or down. Therefore, the two forces must be equal. And this is the result of what happens. So afterwards, this particle is going to enter something called a mass spectrometer. Mass spectrometer. So basically what it is at the end of this area, there's a small opening which leads into another area. over here. So I'm going to draw that down here because it'll give me more space. So in this little opening, what happens is the particle enters, and again, that was a positively charged particle. So the positive charged particle enters here, and what happens is the electric field is removed, and all that's remaining is the magnetic field. So we keep the magnetic field as is. Magnetic field. We're not going to change the magnetic field. I mean, we could, but we'll just keep it the same for argument's sake. And the electric field is gone, and you should also be seeing now we have a positive charge moving to the right in a field that points into the paper or into the screen. Which way is your palm going to be facing? As I pick colors, let's go pink. Hopefully you realize that the magnetic force is up, F sub B, and that also means that it will move in a circular path from our previous homework. Which means, guess what we can do? We could do a little sum of the forces that cause the mass to move in a circle. And we have only one force, the magnetic force, causing the mass to have a velocity in a radius of circle R. BQV equals mv over R. You can divide out an R. And please realize that this electric field over here, I'm sorry, this velocity here is the same as the velocity here. Yeah, this is not an equation to memorize. The end result, BQ equals mv over R, is, again, the result of doing an FBD, doing the sum of the forces, and it leads us to BQ equals mv over R. We could take the velocity from this part of it and bring it back to here, or vice versa. And that's basically it. A couple things that we do need to talk about conceptually. So what I'm going to do is I'm actually going to delete this whole screen. So if you need any more time to pause. A couple things about that velocity selector. Draw it much bigger. And I'm going to get rid of all the noise so we could just focus on the movement of the positively charged particle, which was going straight into this little opening over here. In our free body diagram, if I remember correctly, we had the magnetic force up and we had the electric field force down. When these two were equal, the object went straight. So what we didn't talk about was what happens before it reaches the velocity selector. Over here, way before this, is an electric field where these positive charges are placed. And these positive charges do have different masses, but they are released in the electric field and they are accelerated to the right here. Now, that's its own problem. We can make this a three-part problem if we wanted, but we're not going to. But basically, those particles are accelerated, and what we want to know is we want to make sure the speed at which they enter this opening here are all the same. So we have two equations here. Or two forces. We have the magnetic force and the electric field force. One of these is affected by speed. I think you know, I hope you know, that it's the magnetic field force because that's BQV, whereas the electric field force is just EQ. So what happens if it goes too fast? Like say these particles enter at a speed that is greater than what we got. It's greater than E over B. Because in the previous, we said that the velocity here, when they go perfectly straight, is just the ratio of E to B. But what if it's greater than E over B? What happens to the magnetic field force if the velocity is increased? Please don't overthink this since it's BQV. If the velocity gets bigger, what happens to that? Yeah, it gets greater. So that means the magnetic force will be greater than the electric field force. And hopefully you can tell from this diagram that if that's the case, it will start to deflect up. But what if it's going too slow? So let's say that the velocity is less than E over B. That means that, again, if the velocity here decreases, the magnetic force should also decrease. And if that's becoming less, then Fe becomes dominant and the particle will go down. That's when Fb is less than Fe. So that's why it's called a velocity selector. If the speed is exactly the ratio of the electric field to the magnetic field, the particle will go straight. But if the speed is anything other than E over B, it is deflected and is not allowed to pass through this tiny little opening. That guarantees that we have the exact velocity, and we can know the exact velocity just by knowing what the electric and magnetic field strengths are. Hence, velocity selector. Now, another thing is the mass spectrometer. So here's our mass spectrometer with our magnetic field, which we had going into the screen or into your paper. So let's say you have a light particle and you have a heavy particle. They both enter because, remember, mass was not part of the velocity selector equation that we ended up getting, which was velocity is E over B. Remember, don't memorize that, but that was the final result for that velocity. And the charge wasn't a part of it either. So it basically just came when we got here. We end up with BQ equals mv over r. So let's think about this. Let's assume they all have the same charge for argument's sake, but one has a much bigger mass than the other. So we have one particle that enters, it's got a tiny mass, and I'll just draw this. This is a very small mass, and it makes a turn with a radius r. What do you think would happen if the mass was much bigger? What would happen to the radius of this circle? Take a minute to think about it, but you're driving at 60 miles an hour. That's actually way too fast. You're on a bike and you try and make a sharp turn. You're going, I don't know, 10 miles an hour. Now you're in a fully loaded dump truck. Think about trying to make a turn with something that large at the same speed. Do you think you'd be taking a turn with a wider radius, the same radius, or less radius? Hopefully you're guessing a larger radius. So this is a larger mass. And depending on where it hits this detector distance, that's how they know, that's a distance d. That's how they know the size of the mass, wherever it hits a detector plate over here. Also, the math over here tells you exactly what's going on. Because if B and Q are the same for all particles, just for this assumption, and V is the same for all of them, if the mass gets bigger, then, sorry, that's supposed to be bigger. I don't know what that is. If the mass goes up, that means the radius must also go up. So this mass spectrometer works based on where the particles are hitting detector plates. And that's basically the velocity selector mass spectrometer. I've also included another video for you to watch. It's actually a pretty decent animation of what's going on, and they talk about why it's important in forensics and how they can tell what certain elements are by taking things and making them a gas. It's actually pretty interesting and a good use of magnetism. So anyway, that's about it for this one, and I hope you're all doing well. Of course, if you have any questions, you know where to find me. Take care.